last Today is the last webinar of the series Mind, where we were discussing about math for artificial intelligence and data science. So today we have with us Dr. M. Rajesh Kannan. Many of you might know him. He's a professor in IIT Hyderabad, and majority of his work is concentrated in graph theory. So today we are extremely grateful to have him here with us. His PhD was from IIT Madras, and when you go through his profile, you can see that he has done postdocs from many of the foreign institutes, and many well-known projects are under his name. And to talk about Rajesh Kannan sir's attitude, he is always very friendly to impart knowledge. So I'm very glad to welcome you, sir, to our Minds 24. This is a small gathering. But we are very happy that you accepted our invitation and felt like supporting us. Thank you, sir. Over to you and welcome to you, sir.
Okay, yeah, thank you. Thank you. Okay, can you see my screen? I have shared.
Yes,
something.
sir. Yes, your screen is visible. Now, Laplacian Matrices and Applications. That's
Okay. Yeah. So as the title, yeah, thanks for the invitation and thanks for the nice introduction. So, I'll be speaking about Laplacian matrices of graphs and their applications. Okay, so let's. So this is a brief outline. I would like to introduce a problem. It's called the spectral graph partitioning problem. Okay. So we'll see that this graph partitioning problem is not an easy problem to solve. Okay, in terms of computational complexity, it is one of the hard problems. And then we will introduce the notion of Laplacian matrices, and we'll try to give we'll try to solve this problem in a relaxed setup. Okay, so that is the spectral partitioning. So it's a way of partitioning the graph. That's the bits of the graph. Okay. And then I will, if time permits, I will introduce the notion of clustering. What is the clustering problem? Like again, we will see like clustering is not easy to do, and we will see using the Laplacian matrix of the graphs how to do the clustering. Okay, that's called it's known as spectral clustering. So these two notions like a graph partition problem and then spectral clustering or clustering. It's one of the major concept in data science and machine learning. So I'm not going to say like. Yeah, I think I have written some of the lectures previously, which was in this series. I think you have enough like motivation or enough reasons to consider clustering or partition of partition problems. Okay, I'm not going to say anything about data sets and anything. Just I'll formulate that problem as a mathematical problem, and we will try to see how to solve them. Okay. Okay, so and one more thing, I think you can unmute yourself if you have any doubt. You can either unmute or you can raise your hand. We can discuss. So let us first introduce what is the graph partition problem. So I assume all the audience know a little bit of linear algebra and a little bit of graph theory. Okay. Okay. See my video also. Yeah. So graph partitioning problem is the following. Okay. So you take a graph v comma e. Okay. Throughout this talk, we will assume the graph is trying to use. So throughout this talk, our graphs are simple weighted graphs. Okay. So what do we mean by what do I mean by simple finite graph? So simple means our graph does not contain any loops or multiple edges. And weighted means every edge of the graph will have some weight. Let's assume a positive weights. Okay. And it's a finite graph, of course. Okay. So we don't have infinite graphs. Now, this is the problem. We have to partition the vertex set of the graph into various parts. Okay. So we have to partition the vertex set into k parts. Let's say V1, V2 up to Vk, subject to the following two conditions. Okay. So if you take the union of all these sets, V1 union V2 union up to Vk, then you will get the entire vertex set of V itself. And then the elements of this partition set should be disjoint. Okay, the pair is disjoint. Va intersection Vj should be non-empty whenever you have I not equal to j. Okay, so the problem is easy to state, and we have one more constraint. We don't want to partition the graph into arbitrary way. There is a restriction that all the Va should have almost equal cardinality. Okay, so So if the number of vertices, let's say n, if it is a multiple of k, then every set Vi should contain n by k elements. Okay, that's the only constraint we have to we are imposing. Okay, so that's called the balance constraint. Okay, so cardinality of Vi's are almost same. Okay, if n is a multiple of k, then we can divide the vertex set into n by k parts. So with each part contains n by k elements. Okay. If n is not a multiple of k, then we can choose like some of the sets. If you take any two sets, there the cardinality difference should be at most one. Okay, the difference should be at most one. Okay, that's what. So maybe mathematically we can phrase in this. Okay, so if you take a cardinality of Va, if you take any set cardinality of Va, okay, then that number of elements, the cardinality of Va should be less than or equal to 1 plus some epsilon times cardinality of the entire vertex set divided by k. So k is the number of partitions we want. Okay. Yeah, this is mathematical way of writing whatever I said briefly. So now we need two more notations. So one is so for a given Va and Vj, okay, the partition is given to you. So V equal to union over I equal to. So this is the setup. So for this definition, okay, V is given to you. V is the union of these sets. V equal to 1 to k, Va. Okay. So in this, among this collection, for I not equal to j, let us define a new set Eij. Okay, Eij of Vi comma Vj. This is just you collect all the vertices, all the edges which are having one end in Va, the other end in Vj. Okay. So E is a collection of all edges Vi comma Vj such that one end is in Vi, the other end is in Vj. Okay. So for an example, pictorially, if you take, if this is, let's say Vi, and this is Vj, this is some Vk and so on. Okay. Basically, you are counting, not counting, you are collecting all the possible edges between the vertices Va and Vj. Okay. Similarly, one can define Ejk also. You collect only the vertices, edges which are having one end in Vj and other end in Vk. And for every possible pair of vertex partition, you can define this set. Okay. And we are going to associate a number with it since we have our graphs are weighted graphs. Okay. So W of Eij. So this is going to give me just the sum of the weights of all these edges. So every edge here it is having some weight. Okay. So it may have here it may have W1 and so on, W1, W2 and so on. So you just take sum of all these edges. Okay. You call that as Wij. Okay. So this is Wij. Okay, just sum of all these possible edges between the vertex partitions Va and Vj. Okay. So now what is the question? Our goal is to find a vertex partition P of size k. Okay. It's a balanced partition such that the sum of the edges between these various partitions should be minimum. Okay. So Eij, remember Eij stands for just the set of edges between the vertex sets Va and Vj. Okay. For all possible Va and Vj, you are just measuring the weight. Okay, that is just summing the weights of all the edges. And your goal is to find out a vertex partition, okay, k such that a vertex partition of size k such that this quantity, this summation over summation I is strictly less than j, this W of Eij is the minimum, least among the rest of them. Okay. So the problem is it clear? The problem is easy to state. I hope the problem is clear to everybody. So if you have any doubt about the problem, questions about the problem, you can ask. Okay. And unfortunately, this, yeah. Okay. So unfortunately, this problem is not easy to solve. Okay. So if you know the complexity theory, this problem is a NP-complete problem. Okay. Even for balanced bipartition. By balanced bipartition, I mean I have to just to partition the vertex in two parts, V1, V2, such that this W of E1, E2. Okay. E1, 2. Sorry, not E1, E2. E1, 2. Okay. So even if you take k equal to 2, even for the case k equal to 2 itself, the problem is really hard to solve. Okay. So when you have this type of problems, when the problem is in the complexity, has problem complexity, or is in the complexity class NP complete, then those problems are really hard to solve. So suppose if you can give a polynomial time algorithm to solve this type of problems, then you are going to show P equal to NP. Okay. So many of the combinatorial problem, like the max cut problem and so on, many of the problems are in this class NP complete. Okay. So whenever you have this type of hard problems, naturally, what will you do? So you have to go for some relaxations. Okay. Or can you find out a solution, approximate solution to this problem? Okay. So this is where linear algebra is coming to picture. Okay. So I think our audience is or with the various background. Okay? Maybe some of you might have already seen the notion of adjacency matrices. If you don't know, so this is the matrix associated with the graph. Okay, you just start with the matrix. Start with
Sir,
the, yes, yes.
sir, you have stated the problem. Can you give one or two motivations? Why do we want to study that problem?
So this problem is like basically like when you have a network, let's say when you have a network, I just wanted to group a similar type of people in the network in same part. Okay. So like so like in social networks, maybe for between suppose two people are friends, or suppose two pages are having some link, the links can be given some weight. Okay, or the friendship or whatever relation between two people can be given some weight, whether they are really close friends or okay, they know each other, those type of things. Okay, some weights you assign, or in terms of just Euclidean space, if you want to see, just you can take a set of points, just like define the similarity or some sort of similarity to be like distance between them. Okay, so now I want to group them into k parts. Okay, such that the weights of the like different VIs. Okay, different VI and VJ. Okay, the weights between VA and VJ should be minimum. Okay, or in terms of this points in Rn, if you take the distance between those two points should be maximum. In a way, like you are clustering the points which are close to each other. In a way, partitioning your points, okay, such that the points which are sitting closer, they will be in same VA. The points which are far, they will be in different VAs. In terms of like social networks, if you see the people, those who know each other closely, they will be in same cluster, same group. Okay, yeah.
Right. Thanks.
Yeah, this is one possible motivation. So for this type of problems, one can give like if you see the literature. I'm not an expert in ML or data science. Like I just learned whatever is needed where we are applying all these things. Okay, so each paper will motivate from you can take motivation from various directions. Okay.
Okay. Okay. Thanks, sir.
Yeah.
Please.
So yeah. Now, you see, the adjacency matrix is one of the very basic class of matrix associated with the graph. Okay, so for us here, we'll start with a simple graph. Okay, let's say the graph is the order of the graph is n. That is, there's a graph on n vertices, and the vertex is given by v1 to 1 to n or v1 to vn. Okay, and we are going to associate a n by n matrix with the graph. Okay, G is a graph of on n vertices. We are going to associate a square matrix n by n matrix with that graph. So how do we define this n by n matrix? So the ijth entry of the matrix is denoted by aij. So I had to define what are the entries. So all the entries of the matrix aij are either 1 or 0. Okay. So we are going to keep a 1 over here. Ijth entry we are going to keep a 1 if the corresponding vertices I and j if they are adjacent. Okay. And we are going to keep a 0 over here if they are not adjacent. Okay. So you have a graph, corresponding to the graph, you are going to associate a matrix. Okay. So if you are seeing it for first time, then let me give some examples. So you consider this graph, okay? So this fits into our setup. This is a finite simple graph, okay? So simple, finite, undirected graph. So for this graph, I'm going to associate a adjacency matrix. So how to do that? So both rows and columns are indexed by the vertex set. Okay, so you can see here. This is 1, 2, 3, 4. 1, 2, 3, 4. Okay. So between the vertices 1 and 1, there is no edge because we are working with simple graph. None of the vertex has edge from edge to itself. Okay. So 1, 1 entry is 0. 1, 2 entry, we have an edge between the vertices 1 and 2. So you have 1 here. And between the vertices 1 and 3, you have an edge. So you'll keep 1 here. And between the vertices 1 and 4, you have an edge. So keep 1. Similarly, fill the rest of the entries. Just one more entry I will explain. Look at the fourth entry. Between the vertices 2 and 4, you don't have an edge, so I'm keeping it 0. Okay. Also, you look at the diagonal entries. All the diagonal entries are equal to 0. The reason is it's a simple graph. You don't have any loops in the graph. Now, yeah, so it is easy to see that this graph, this matrix A of G is a symmetric matrix. Okay, because whenever you have an edge from the vertex I to J, then you do have an edge from J to I. Okay, so this is a symmetric matrix. So what's the reason to emphasize the fact that it's a symmetric matrix? So the first course in linear algebra will tell you the symmetric matrices are one of the interesting class of matrices. Interesting from the point of view that all the eigenvalues of the symmetric matrices are real, and you do have a set of eigenvectors which will form an orthonormal basis for the space Rn itself. Okay. So some of the basic properties one can observe from the adjacency matrix. Okay, basic properties about the graphs one can infer from the adjacency matrix is that the first one is symmetric. It's sort of trivial. We can observe from the definition. Okay. Now, if you take the sum of 2 by 2 principal minors, okay, of the matrix A, then that should be equal to negative of number of edges. So what is the meaning of it? So adjacency matrix is an n by n matrix. Okay. So I guess all of you know what's a 2 by 2 submatrix. By principal submatrix, it's just a jargon. Okay. So this, like, just take the ith row and the jth row, ith column and jth column. That means if you take 2 rows, you have to take the corresponding 2 columns. The same columns, ith column and the jth column. So if you are taking 2 by 2 arbitrary submatrices, then like you don't have to restrict on ij. Here you can take ij, and here you may take k and l. Okay. For principal submatrices, I had to choose the same columns. Okay. So look at the entries which are sitting in the intersecting point. So this will be a 2 by 2 matrix. Okay. Just to compute the determinant of this matrix. Okay. So that's called a 2 by 2 principal minor. Okay. So sum of all 2 by 2 principal minors means like you find out all possible 2 by 2 principal minors. That is, you have n choose 2 choices. Okay, for every n choose 2 for each n choose 2, each of the n choose 2 principal submatrices, find out their minor. Okay, so here things are very really simple. What are the entries of this 2 by 2 matrix? So ith row, jth column, ith row, jth row, ith column, jth column. So ith entry and the jth entry, they are 0 because they are coming from the diagonal entries of this matrix A itself. And corresponding to the off diagonal entry, you will get either 1 or 0. Okay, there are only two possibilities. 0 will put here when I is not adjacent to J. So in that case, your determinant is equal to 0. The principal minus is equal to 0. And you keep a 1 here when there is an edge between the vertices I and J. Okay. So corresponding to every edge, okay, if Ij is an edge, then corresponding to Ij, I'm going to get a -1 here. Okay. So that means that whenever I have an edge, then I'm getting a -1 in this sum of 2 by 2 principal minors. In this sum, I get a -1. Hence, the sum of all 2 by 2 principal minors is equal to negative of the number of edges. Okay. So this is an interesting result. The reason to say this is an interesting result is one side of this result is about graphs, and the other side of the result is about the adjacency matrix. It's a proper result connects matrix theory and graph theory. Okay. And like the matrix A is a square matrix. Okay, it's an n by n matrix. So if you have an n by n matrix, then you can talk about its powers. Okay, so then whether the kth power of this matrix A, does it have any combinatorial information about the underlying top? Okay, so natural question one can ask. Okay, so in fact, the ijth entry of the matrix A power k, this will give you the number of walks of length k between the vertices I and j. Okay, so note that A power k is an I hope we can see this color. Bad choice. Change it. This block here. Let's go here. A power k. So this is Aij. This is a notation. I'm not meaning Aij power this bracket k stands for the ijth entry of this matrix k. So this quantity counts the number of walks of length k between the vertices I and j. Okay, this is one of the interesting result. Suppose if you take if you apply this result for a square, then you can see something some interesting thing. So a square, if you see, what will be the diagonal entries of a square? So number of if I look at the 1 diagonal entry, that will give you number of walks of length 2 from the vertex 1 to itself. Okay, number of walks of length 2 from the vertex to itself is just the number of edges which are incident with it. That is nothing but the degree of that vertex. Okay. So in the matrix A square, if you see the diagonal entries, all the diagonal entries are degrees of the corresponding vertices. Okay. So degrees of the corresponding vertices. So I think most of you know what is the definition of trace of a matrix. Okay. So what is the trace of this matrix A square? So the trace of this matrix A square is just the sum of the diagonal entries. Okay. And all of you have done a course on graph theory. Okay. What's the sum of all the degrees? This will give me twice the number of edges. Okay. And the basic course in linear algebra will tell you trace is also nothing but sum of the eigenvalues. Okay. So if lambda 1, lambda 2 up to lambda n are the eigenvalues of your matrix A. Okay. If they are the eigenvalues of A, then what are the eigenvalues of A square? Just you square them. Okay. These are all the eigenvalues of A square. Okay. This will tell me summation lambda I square I equal to 1 to n. This quantity equal to twice the number of edges. Now you get some interesting expression. Okay, let me take some other color pen. Okay, so what is the interesting observation? The number of edges in the graph is same as half of, you take all the eigenvalues of your matrix, okay, take it off. You see, this is a proper spectral result. So number of edges is a commutative quantity. You have to count the number of edges in your graph. Okay, that is half of, just square all the eigenvalues and sum them. Okay. So if you know all the eigenvalues of your given graph, then you know how many edges the graph is. Okay. So just this is the kind of basics of spectral graph theory. I'm sorry, basics of spectral graph theory I'm explaining. Okay. So yeah, many more results, like just I'm giving just one or two couple of results only. Okay. And the spectrum of the adjacency matrix does contain lot of combinatorial information. Okay, what are they? So all of you know what is the maximum vertex degree and what is minimum vertex degree. Okay. So the spectral radius of any graph, by spectral radius, I mean the largest eigenvalue of the adjacency matrix. Okay, that is at least the least vertex degree and at most the largest vertex degree. Okay? And this is not hard to prove if you know non-negative matrix theory. It's easy to prove. Okay. The second is this is kind of little non-trivial. Okay. So chi of g is the chromatic number of the graph. Okay, chi of g is the chromatic number. The chromatic number means the minimum number of colors required to color the vertices of the graph such that no two adjacent vertices receive same color. Okay. Now, the chromatic number, again, if you see, that's not an easy, computing the chromatic number of the graph is not an easy problem. Okay. Again, this is a NP complete problem, I think. Okay. There's no easy algorithm to compute the chromatic number. Okay. Now, this chromatic number of G that has an like a spectral bound. Okay, so the chromatic number of any graph G is less than or equal to 1 plus lambda 1 of G. Lambda 1 is the largest eigenvalue of the graph G. Okay, so if you see the largest eigenvalue, so you have to find out the largest eigenvalue of a symmetric non-negative matrix. Okay, of course, like maybe if you're teaching for BSc or MSc students or BTech MTech students, I think most of you might have seen a method to compute the largest eigenvalue of a matrix. Okay, so called power method. You can use the power method to approximately compute the value of lambda 1. Okay, so you may not be able to find out the exact value of chi of g using this expression. Okay, but you can get a decent bound for chi of g in terms of this lambda 1. Okay, so one side you have a quantity which is really hard to compute. You don't have any polynomial time or any reasonably good algorithm to compute this chi of g for arbitrary graphs. On the other hand, here you have some decent quantity to handle, like lambda 1 can be computed using power method and so on. Yeah. So this is known as a Wilf's bound in the literature. Okay, so I'll give you the references at the end. And similarly, one can give a upper bound, lower bound for spectrum, this chromatic number using the eigenvalues. Okay, so here lambda 1 denotes the largest eigenvalue, lambda n denotes the smallest eigenvalue. Okay, so the chromatic number should be at least 1 minus lambda 1 by lambda n. Okay, so it looks little strange because it's you're going to give you're giving a like upper bound for a lower bound for a non-negative or a positive quantity by 1 minus something, even though it looks minus here, this quantity is this entire quantity is positive because lambda 1 is positive if you take G to be a graph with at least one edge. If lambda 1 is positive, since the trace of the matrix A is 0, so lambda n should be negative. So the proper way to mention this is 1 plus this thing and lambda 1 by minus lambda n. Okay, so lambda n is negative, minus lambda n positive, so you are going to give a positive. And the other thing is, I think most of you know what is a bipartite graph. Okay, bipartite graph is a structural property. Bipartiteness of a graph is a structural property. So this property also can be read out from the spectrum. Okay, that means so lambda is an eigenvalue if and only if minus lambda is an eigenvalue. Okay, if this property holds true for the eigenvalues of the adjacency matrix, then the graph should be a bipartite. Okay, so that's an interesting result because one side you have again a graph theoretical property, and the other side you are seeing something a stronger result about the spectral property. Okay, okay, good. So do you have any doubts so far? Do you have any questions before I proceed? Okay, there is no question. Let me proceed. So one can associate one more class of matrices. It's called the Laplacian matrices. Okay? So it is defined in this way. Just I will directly project that definition. Okay. So I have written something like Laplacian matrix is defined in this way. Okay, but it can be like it can be neatly said in this way. Define Laplacian matrix as using this formula. L of G equal to D of G minus A of G. Where D of G is the degree matrix. That means that it is a diagonal matrix whose diagonal entries are degrees of the vertices. Okay? D of G is just degree of V1 or 1 and so on, degree of Vn. All the diagonal entries are degrees of the vertices and keep zeros in all the rest of the places. Okay? So this matrix is defined using, Laplacian is defined using this D of G and A of G. Okay? So A of G we know already how to define A of G, and D of G we are defining over here. Okay? So this is a matrix like a kind of this matrix you will see in many of the applications. This Laplacian. Okay, so this matrix has a lot of interesting properties. So today, like I'm not going to state a lot of properties of this matrix L of G. Okay, and maybe just to motivate you, like what is why I say this matrix is interesting. Maybe I will tell you just one application. So I think most of you know Cayley's formula, right? What is Cayley's formula? Oops. What is Cayley's formula in graph theory? The number of spanning trees in the complete graph, Kn. How many complete graphs this graph has? If you have to count the number of spanning trees in the complete graph, number of labeled spanning trees, let's say, labeled spanning trees in the complete graph, how many such spanning trees will be there? So this is n power n minus 2. Okay, when you are doing a first course in graph theory, you might have seen this. Okay. Now, if I take an arbitrary graph, let's say G is an arbitrary graph, can I have some nice formula like this, this Cayley's formula for an arbitrary graph? So unfortunately, for many of the graphs, you don't know in combinatorial way of giving or deriving a formula for number of spanning trees in the graph. But using this Laplacian, you have a very interesting very interesting formula. So the formula says that you look at this matrix L of G, okay? You choose any of your favorite entry from this L of G. Okay, any entry from this L of G you choose and remove the row corresponding to the entry and remove the column corresponding to the entry. Okay, after removing the row and column from that matrix, you will end up with getting a n minus 1 by n minus 1 submatrix. Compute the determinant of the matrix and apply absolute value to that. Okay, so you will get a number. Okay, it's an integer matrix, so we are going to get an integer. Okay, that positive integer will tell you the number of spanning trees in your graph. Okay, so that is, if I had to count the number of spanning trees in an arbitrary graph, just I had to find out the determinant of, so Laplacian denoted by L. Okay, this open bracket I am using for remove the ith row, remove the jth column. Okay, so by this I will get a matrix n minus 1 by n minus 1 square matrix. Compute the determinant of this matrix. Okay, take the absolute value. Or just I can say cofactor, if you are comfortable with the notion of cofactor, minus 1 power I plus j, that's also will work. Okay, this quantity will give you the number of spanning trees in the graph. Okay, labeled spanning trees. This is again amazing. The reason is it's a matrix theoretical quantity. L of g, even though we are getting from the graph, this determinant and all, like all of sudden it is showing, and then like you are getting a nice formula for the spanning tree. This is called the matrix tree theorem or the Kirchhoff's law. Okay. So this is an example. Okay, this is like some people are waiting. Someone can admit or I'm showing. Okay. So consider the graph. This graph on 4 vertices. You have to see what is the degree matrix. Okay. So corresponding to the vertex 1, you have degree 3. Okay. Corresponding to this vertex, you have degree 3. Okay. Degree of the vertex V1 equal to 1 equal to 3, and so on. Degree of the vertex 2 equal to 2. Degree of the vertex 3 equal to 2, and degree of the vertex 4 equal to 1. Hence, every vertex is having, hence you can find out all the degrees of the vertex 3, 2, 2, 1. Okay. Just to subtract the adjacency. Adjacency matrix we have already seen. This is a illustrative example. Okay. So now I'm going to say some of the properties. Okay. So first property is the row sum and column sum of the Laplacian should be equal to 0. Okay, that's a trivial fact. You can just, by looking at the matrix, you can say. So if you take any row of this Laplacian matrix, what is the diagonal entry of that matrix? The diagonal entry of the matrix is the degree of the particular vertex. Okay. The diagonal entry of that matrix is degree of the particular vertex, which is a positive entry. Okay. And how many minus ones you have in this particular row? That is number of neighbors. That's also same as degree. Okay. Suppose if here you see 3 is the degree of the vertex 1, and you have 3 minus 1s because it has 3 neighbors. So this is when you sum this, then it is going to be 0. Since it's a symmetric matrix, if the row sum is equal to 0, then the column sum also equal to 0. Okay. Hence, for the Laplacian, if you take row sum and column sum, both of them are 0. Okay. So if you're attentive enough, then you can say that the Laplacian is always a singular matrix. Okay. So L of G, if I give this big one for all ones matrix, all ones vector, okay, then I will get this is 0 times all ones vector. That is, this is the eigen equation corresponding to the eigenvalue 0. The all ones vector, if you take, then that's an eigenvector corresponding to the eigenvalue 0. And the second property, okay, which I would say, like those who want to apply the spectral techniques in any of this machine learning or data science or artificial intelligence field, or if you're already working on those fields, this expression you will see in almost any of the application. Okay, this is one of the crucial inequality or crucial expression, the formula for the quadratic form, which you will find out. Okay. So X transpose L of X. So I think most of you know what is the meaning of a quadratic form. I don't have to define what's a quadratic form. Okay. So this is an X is an L of G is an n by n matrix. Okay. L of G is an n by n matrix. So X is an 1 by n vector or n by 1 vector. Here I'm using X transpose. So this X transpose L of G into X, this gives me a number. Okay. Okay. This is not visible. Yeah. So this is a number. And something you can see here. You see, this is the sum of squares. Okay. So every entry is the sum of squares. Every entry is a square. So hence the entire quadratic form is the sum of squares. So this quantity is always greater than or equal to 0. Okay. So already you know L of G is symmetric. L of G equal to L of G transpose, because adjacency matrix is a symmetric matrix. And our matrix, the D of G does not play any role in distinguishing the symmetricness. Okay. So L equal to L transpose, that is easy to see. Suppose if a matrix satisfies these two conditions, and we do have a name for this type of matrices. What's the name? So if a matrix is symmetric and the quadratic form associated with this matrix is always non-negative, then this type of matrices are called, what's the name for this type of matrices? Positive semi-definite matrices. So that means that all the eigenvalues of this matrix are non-negative. Yeah, you have any questions? Okay, I can't see any questions. Okay, so I'll just try to give a simple proof of this. Okay, so even though like if you are not applying this thing, okay, so the third property is just a simple application of the second property, L equal to L transpose, and yeah, that's what that we have seen. If you take the property 2 for granted, and the third one is it's just an online consequence of what we have discussed today. Okay. The proof of 2 is also really simple. Okay. Just I will briefly tell you. I'm not going to read out the slides. Just apply this decomposition. Okay, L is given by D minus A. Okay, and then just you can use this bilinearity of this or you can just use this quadratic form, bilinear quadratic form, just to component wise you split them. Okay, and then I just express these things. Okay, D is the diagonal matrix. Then you will get summation I equal to 1 T and dA into xi square, and this X transpose AX. Just if you calculate this quadratic form associated with the adjacency matrix, this is what we are going to get. Then just cleverly you have to manipulate this. Just to get a sum of squares expression, okay, cleverly you can manipulate it. Okay, what I'm going to do, just this first term I will write for 2 times, okay, and then I will divide it by half. Okay, then I will 2 times dA, 2 times summation dA xi square, I will split it into 2 parts, one with respect to I, one with respect to j. So I and j are just dummy variables. Okay, 2 times dA xi square, instead of writing that, I will write down dA into xi square plus dj into xj square. That's all inside the summation. Okay, and this quantity 2 I have multiplied, that 2 will be here. Okay, and then corresponding to each dA, you expand this expression, you are going to get xi minus xj whole square. It's a school algebra, just but it has a lot of application. Today you will see an application. Okay, yeah, in a couple of minutes. Okay, so the take-home message, at least like who are attending, like if you are not following many other things, just this expression, if you can keep in your mind, if you are doing something, anything related to this Laplacian, if you see any application of this Laplacian matrix in your literature, mostly it will be using this expression. Okay, okay, and yeah, so I was preparing this talk for a group of mathematical audience. Okay, expecting that, but nevertheless. I'll just explain only the statement. I'm not going to give the proof of the statement. Okay. So this rank of this Laplacian matrix will give you the number of connected components. Okay. So since it's a symmetric matrix, so rank of this matrix is same as. So rank of the Laplacian of the matrix is same as n minus the algebraic multiplicity of the eigenvalue 0. Okay, note that 0 is always an eigenvalue of the Laplacian because all one's vector is an eigenvector corresponding to the eigenvalue 0. This theorem says that if the eigenvalue 0 has multiplicity k, then the number of connected components should be equal to k. That's what it says. Okay. The theorem is written in terms of, if you know the rank-Nelldy theorem, the theorem is written in terms of rank. Okay. So if the rank of the matrix is n minus k, then what is the multiplicity of the eigenvalue 0? That says that multiplicity of algebraic multiplicity of the eigenvalue 0 is equal to k. Okay. If 0 has multiplicity k, then it should have k connected components. In other words, the graph G is connected if and only if the second smallest eigenvalue should be different from 0. Okay. So people say people have found out there are a lot of generalization of this result in the sense that people used to say this is called robust version. So if your the second smallest eigenvalue of the graph, if it is different from 0, then the graph is connected. But the magnitude of the second smallest eigenvalue, even though it is different from 0, it can be close to 0. Okay, in that case, your graph will be not well connected. Okay? If the second smallest eigenvalue is really high, then in that case, your graph will be really well connected. Okay, if you want a precise definition of what is well connected and what is not well connected, just you can use this vertex connectivity notion. Okay, so if you know the notion of vertex connectivity, just I'm giving a notion of alpha of v, the minimum number of vertices you have to remove so that after removing these vertices, your graph will become disconnected. Okay, so this quantity is bounded below by the second smallest eigenvalue of every one. Okay, second smallest eigenvalue of the Laplacian. So if the second smallest eigenvalue of the Laplacian is really high, then that forces that the vertex connectivity is really high. Okay, the proof is not hard. Okay, you can find out the proof in any of the spectral graph theory text or lecture notes. So I have in the end of this lecture, I will give you a collection of references where you can find out all these proofs. Okay? So now, as I said, like I'm not going to give a proof of this statement. Okay, but I hope I will circulate. I will send the slides to the organizers. I think if you want, you can get it from them. Okay, the proof is routine proof in spectral graph. Okay. So now, yeah, I think I was told I can take at least 1 hour. Okay, maybe I will take it's around 45 minutes or over. I'll take some. So let us jump on to the real application. Okay, and I think it is whatever I'm presenting. It is no way related to like the state of art, whatever people are doing today. Okay, so this is the paper which appeared in 2008 or 9 sometime back, some survey paper by Van Ulrich. She's a German mathematician and data scientist. Okay, so my aim in this lecture is to explain the mathematics behind what people are using. Okay, using in the machine. Okay, so I hope you remember the problem which we started, the problem the motivating problem which we considered, partitioning problem. You had to partition the vertex of the graph into k parts such that the weights of some of the weights of the crossing edges is minimum. Okay, so let us look at a toy version of the problem. Okay, toy version means easiest version of the problem. I just want to bipartite my graph V into V1 union in V2. Okay, and if you remember that equality constraint that says that both of the partite sets should have almost same number of edges. So here to make our life simple, I am taking this spectral part. I am taking the number of vertices in the graph to be an even number. Okay, so that I can partite them equally. Yeah. Any question? Okay, let's move on. So the slide is really interesting and important. Okay, just give attention to this. So I'm going to associate a vector with this bipartition. Okay, so n vector. If it is a graph on n vertices, I'm going to associate a n vector with this bipartition. The association is really simple. Okay, so x is a plus or minus 1 vector. Okay, that means that every entry of this matrix, this vector x is it's a number, either it is plus 1 or minus 1. I'm going to keep a plus 1 here if that vertex is in the partition V1. I'm going to keep a minus 1 if the vertex is in the partition V2. Okay, so it's really simple. It's a kind of, you can think of characteristic vector of V1 or V2 up to this. Instead of 0, keeping zeros and minus 1. That's all. Okay. Now, I will evaluate this quadratic form. So if you remember when I stated this is one of the very important quadratic form, you will see again and again and again. So for this particular vector x, if you evaluate this quadratic form, what's happening? So this quantity equal to 4 times the number of edges which are starting from V1, which are ending at V2. So how to see this? Okay. So V1 is here. V2 is here. Okay. Now the edges are crossing from V1 to V2. Okay. So suppose if I take 2 vertices which are part of V1 itself. Okay. If 2 vertices, if both of them are in V1, what will be the corresponding xi's? Okay. Let's say I1 and I2, if both of them are in the same partite set, then both xi1 as well as xi2, both of them will receive the same number. So in this case, 1 only you will receive. Okay. Similarly, if I1 and I2, both of them are in V2, then again you are going to get -1 for both of them. Now look at the quadratic form. In x transpose Lx, okay, I'm running the summation over all the adjacent vertices. Okay. If I1 and I2, if both of them are the same component, they are going to receive the same number. Okay, either 1 or +1, either +1 or -1. Okay. So in that case, this xi minus xj, that will be 1 minus 1 or -1 plus 1. It will be 0. So the edges corresponding to the vertices which are in the same partite set. Okay, those edges will contribute 0 to this. Okay, what are the other entries? Suppose if I have an edge which has one end in B1, the other end in B2. Okay, then what will happen? For one end, I will get 1. For the other end, I will get -1. So this will become something like 1 minus -1, which is +2. The other case is one end is in -1, the other end is also in -1. What I will get? Wait, am I doing some mistake? So one end is -1, the other end should be in +1. Okay, because I'm considering the crossing edges. In this case also, I'm getting -2. So I'm squaring here, so it doesn't matter whether I'm getting 2 or -2. Okay, I'm going to square and I'll get 4. So corresponding to every crossing edge, I will get 4. Hence, total the number of crossing edges we have given as a notation. Okay, E of V1 comma V2. Okay, I'm just using the notation. It should be E of 1, 2 of V1 comma V2. This was the notation I used in the beginning. Okay, just to hear. It's very clear. Only V1 and V2 are there. Okay, so 4 times the number of edges. So now this is the amazing expression. You have the number of edges from V1 to V2. That's an expression. For that, you have an quadratic expression in terms of the Laplacian. Okay. Now you see, in the beginning of the problem, I said the weighted graphs. Okay. So here I'm not assuming any weights. So weights also you can assign and then you can do the same process. What you will get, you will appropriately you will get the weights over here. Okay. Now, minimizing this E of V1 comma V2. What is our ultimate aim? You had to partition the vertex into 2 parts, V1 and V2, such that the weights of the crossing edges are minimum. So in this case, I'm not considering any weights. That means that I'm going to just consider the number of crossing edges are minimum. That's all. Okay? The number of crossing edges are minimum. That's the only constraint given to me. That is, I have to minimize this quantity. Okay. So minimizing this quantity is same as minimizing this X transpose LX over this all +1 -1 vectors. Okay. The reason is I have to find out a bipartition. Given a bipartition, I can associate a +1 and -1 vector, and I can revert this process. When I get a +1 and -1 vector, corresponding to that, I will get a bipartition. Okay. So my problem of minimizing this E1, EI, J. Okay. So this will be minimum. Okay. Only when the corresponding quadratic form X transpose LX, where X is an +1 -1 vector, N vector. Okay. This quantity is minimum. Okay. So this is the important step, I would say, like transforming this combinatorial problem into an optimization problem. Okay. Crossing edges, number of crossing edges is minimized where this quadratic form is minimized over this constraint set. Okay. So if you might have seen this, maybe this may be a familiar or easier way to write down the problem. So I have to minimize this quadratic form X transpose LX, subject to the condition that X transpose 1 equal to 0 and X, all the X's, the components X's are in +1 and -1. Okay. So X transpose 1 equal to 0, if you wonder from that, this as constraint are coming, we are taking cardinality of V1 equal to cardinality of V2. That means that this vector X has equal number of +1s, equal number of -1s. So when you sum everything, you are going to get 0. Okay. That's what that means. Okay. And if you know about integer programming problem, this is a typical integer programming problem. Okay, you have, if the constraints are, the constraints are integer constraints. Okay, whenever you have integer constraints, even though it is only finitely many collection, this problem is again not an easy problem to solve. Okay, so on the other hand, we can go for a relaxed version of this problem. By relaxed version, I mean, so instead of considering this constraints over a finite set, okay, I'm going to consider this constraint on a unit ball, okay, on R power n. So how to see this? So I had to minimize this quantity subject to X transpose 1 equal to 0. This condition I have captured. So instead of doing this Xi belongs to 1 or -1, I'm going to take the 2 norm of this vector is equal to 1 after normalization. But just if every vector is having xi equal to either +1 or -1, that we have a norm, I think square root of n. Okay, just I can discard the square root of n instead of we can manage that. Okay, instead of including that n here, just I'm going to take a vector in the unit sphere of Rn. Okay, because minimizing with respect to xi is 1 by 1 -1, that is same as doing the process for 1 by root n comma minus 1 by root n you can take. Okay. So if a vector consists of a vector whose all entries are 1 by n, 1 by root n, and so on. Okay. Then when you square it and sum them, you are going to get that is in the unit ball of the L2 space. Okay. You don't know L2 space, then don't worry about it. When you take the square of the entries and sum them, if you are getting equal to 1, okay. So this object belongs to such a set. Okay. This is also known as B of L2. If you don't know what is B of L2, don't worry about it. Okay. So now you are having a continuous setup. So in 2 dimensions, this is like a circle. Okay. So you are going to minimize certain quantity over a nice set here. Okay. So this is a non-linear programming problem. Okay. Or in terms of if you I think most of you may be teaching if you are teaching for math or computer science students, you may be teaching some multivariable calculus. Okay. So this type of problems are typical. They will show up in multivariable calculus. So can any one of you suggest which method one can apply to solve this problem? You forget about LPP or you forget about the optimization problem. Suppose if you have to minimize the function, let's say f of x comma y. Here I'm having only f of x subject to a constraint like this. Okay, so f of x means it's an tuple. Okay, x1 up to xn. So do you know any method which will solve this minimization problem? It is in multivariable calculus when you are doing for BTech or BSc MSc students.
Lagrangian method of multipliers.
Yes, Lagrange's multiplier. So I'm going to just solve this problem using Lagrange's multiplier method. Okay. So first you have to form your Lagrangian. Okay. This is your Lagrangian. Okay. So you have to use the object which you are going to minimize. Okay. That corresponds to the first term. Then lambda 1 into first constraint and lambda 2 into second constraint. So this is my first constraint. X transpose 1 equal to 0 and norm square of x is equal to 1. This is second constraint. So both the constraints are captured. Okay. Now what will you do? You have to take the partial derivative, okay, with respect to x and the partial derivative with respect to lambda 1 and the partial derivative with respect to lambda 1. So you do all the partial derivatives. Partial derivative with respect to x, that will give me, just you take that derivative, okay, then you are going to get this expression. Okay. So x transpose Lx derivative, computing derivative is the routine one. Like it's a like maybe you can include this as in a problem sheet when you are teaching multivariable calculus. Okay, so something like x1 square, x2 square, and so on. Okay, yeah. So one can easily compute the partial derivative. The partial derivative will be this one. And with respect to the variable lambda 2, if you take the partial derivative, then you are going to get rest of them will become 0. Okay, only this term will survive. And similarly, if you compute the partial derivative with respect to the third variable lambda 2, then you are going to get this constraint. Okay. So Lagrange's multiplier method says that your solution should satisfy all these things. Okay. So now you look at here from the second constraint, you get x transpose 1 equal to 0. Okay. So if x transpose 1 is equal to 0, you look at the first one. From here, can I say something? That's what I'm trying to see. Okay. So if x transpose 1 equal to 0, if you just to multiply this first equation with x transpose, just to pre-multiply by x transpose, then what will you get? I'm sorry, not x transpose, 1 transpose. So look at this expression. Okay. Just to pre-multiply this quantity with 1 transpose. 1 transpose means take all one's vector and take its transpose. So we have observed in the very first slide, maybe very first slide of Laplacian matrices, the column sums of the Laplacian matrices are 0. Okay. So L1 gives you the row sum vector. 1 transpose L gives you the column sum vector. In terms of Laplacian, both of them are equal to 0. Okay. It's a 0 vector, row vector. This is a 0 column vector. So first quantity will be equal to 0 if I pre-multiply the first equation by 1 transpose. What about the second one? It is lambda 1 into 1 transpose 1. Okay, this is n. And what about this quantity? 1 transpose into x. If you see the constraints I have, 1 transpose x is equal to 0. Right? You see the constraint? X transpose 1 is equal to 0. Just take the transpose of it. Then you will get 1 transpose x is equal to 0. Okay, 1 transpose x is equal to 0. So that will give me this third term is also equal to 0. So that means first term and third term, they are equal to 0. Hence, this lambda 1 transpose 1 should be equal to 0. Okay, but 1 transpose 1 is equal to n. This will be a number. 1 transpose 1, if you compute, that will be a number n. Lambda 1 into n is 0. That means that lambda 1 should be equal to 0. So yeah, among these constraints, in this combination, lambda 1 should vanish. Okay. So I'm trying to explain rigorously. Okay. So so if lambda 1 equal to 0, then this equation, what will happen to this equation? Lambda 1 I can strike out. Then I get Lx equal to lambda 2x. Okay. So now let us rewrite our minimization problem in terms of this new expression. Okay. Remember, we would like to minimize x transpose Lx. Now Lx became lambda 2x. Okay. So x transpose Lx will become lambda 2 into x transpose x. So and x transpose Lx should be equal to lambda 2 also. Okay, means like x transpose, if you pre-multiply with this quantity, we are going to get L transpose x transpose x transpose Lx equal to lambda 2. Okay, so that is the equivalent problem is just I want to minimize this lambda 2, where lambda 2 I'm getting from here. This is the x transpose Lx. In fact, one can show that this is the second smallest eigenvalue of the Laplacian. Okay. So first smallest eigenvalue, that is that is always equal to 0. So now this lambda 2, there is one thing I'll tell you, something called variational characterization. So lambda 2 is equal to, you just minimize over all the norm 1 vector which are orthogonal to all ones vector, okay, x transpose Lx. So this is the formula for the second smallest eigenvalue. Okay. In fact, this minimization problem, whatever we have stated, this is same as this minimization. Okay. This problem. Okay. So now we have to minimize this x transpose Lx. Okay. That quantity is nothing but lambda 2 for us. Okay. So now the problem is solved. Now how to find out the solution? So remember, we started with the graph. We have computed the Laplacian, okay, and corresponding to the Laplacian, we have figured out that minimization problem. This x transpose this x transpose Lx, the minimum will be obtained for wait, what's the problem? Let me go back to the problem. Okay, for the relaxed version, like the minimum we are getting as a lambda 2. Okay. Now the heuristic, okay, or the solution to the proposed problem. Okay, I'm saying this is the heuristic. I'm just because this is not a solution. Okay, this is not an algorithm. This will always give a solution. Okay, so if we take the x to be the solution vector of the equivalent problem, that is the eigenvector corresponding to the eigenvalue, second smallest eigenvalue. Okay, then all the entries of the eigenvector are, of course, real numbers. Okay, we are dealing with real matrices, real symmetric matrices. So all the eigenvectors, eigenvalues, both are reals. So every entry is a real number for the second smallest eigenvalue. Let us take m bar to be the median of all the xi's. Okay, xi is a set of numbers, n numbers. So you compute the median of these numbers. Okay, and then you are going to give your partition in this way. So keep xi bar equal to 1 if the median is strictly less than m bar, and xi bar equal to -1 if it is greater than or equal to m bar. The way we are defining this median, this will bipartition your entire collection into two parts, where one collection has the value equal to 1, the other collection has value equal to -1. Okay. Now you define your bipartition in this way. V belongs to V1 if and only if xv bar is equal to 1. Okay. That means that if V1 you know, then V2 you take V minus V1. Okay. Needless to say, V2 is nothing but V minus V1. Okay. So this will give a bipartition. Okay. So now this is a heuristic. This is not an algorithm. So I'm not going to prove this. This will always give me a perfect bipartition. Okay. The reason is we don't have any proper algorithm to compute this thing. Okay. This is a heuristic. In many of the cases, this will give very good results. Many of the data sets. Okay. So this is one typical way of converting a machine learning problem or a data science problem into a linear algebraic problem, and use linear algebraic tools to solve that problem. Okay, so if you know about something called singular value decomposition, similar type of things you might have did for something called handwritten digit classification algorithm. Okay, you will use the singular values and singular vectors over there. Okay, so and many more. There is another problem. It is called a clustering problem. Okay, so basically these two are kind of similar problems. Okay, that I'm not going to take more time. Just I will explain the problem and then I will wind up. Okay, this already is 7. Okay, yeah. So we have some set of points. Okay, x1, x2 up to xn, and we do have a similarity measure. Means between 2 points, how they are similar, okay, how much they are similar. So this can be thought of as again points in n-dimensional space or in your Facebook network or in Twitter network or somewhere like between two people. Like if you have a friendship and unfortunately we don't have any way to measure the friendship between them. Okay, but it's like if there is some parameter like if you have cities or if you have some group of some buses or something, you can measure the similarity in some way. Okay, Sij, some non-negative number. Okay, again mathematically, if you want to see, like you can take n points in the Euclidean space. Okay, just to measure the distance between them, define Sij to be the distance between those vectors. Okay, Si, Vi and Vj. Okay, given any data. Okay, suppose if we can represent them, if you with some similarity measure are there, then one can neatly ask this question. Okay, so I have given you some similarity measure. Based on the similarity measure, can you divide the entire data sets into several groups? Maybe the several groups will be also given to you. How many groups I want? Suppose I'll give you like a 1 lakh data point. Okay, I want to just group them into 1,000 groups or 100 groups. Okay, how to group them with respect to the similarity measure? This is one of the routine problem, one of the classical problem in clustering. Okay, or this is the clustering. Divide the data points into several groups such that the points in the same group have similar and the points in the different groups are dissimilar to each other with respect to this similarity. Again, this problem is not an easy problem. Okay, so one can define the notion of a similarity graph. Okay, just I'm going to so just using using this data set again, you are going to formulate a matrix. Okay, so first of all, we have to form a graph. Okay, from the graph you can construct a matrix. Okay, again we are going to consider the Laplacian matrix of the graph. So definition of graph is really simple. Okay, you take, if n points are given, then keep them as vertices of the graph, and you are going to connect all the vertices, all possible edges with the weights Sij. Okay, this is one way of doing. Okay, the other way of doing is you don't have to draw the complete graph. Okay, you don't have to draw the entire graph. Instead of drawing the entire graph, you do one thing. Just you keep a threshold. Okay, suppose Sij is greater than or equal to certain quantity, then only I will draw a weighted edge between those graphs. Okay. So in this method also you can draw associated graph, or you can associate the complete graph also. You can just keep all the SIs as it is. Okay. So there is something called the heat kernel for graph, something e power minus norm of xi minus xj. If you know the data points are in the Euclidean space, by t something should be there, something is there. In that way also one can do. So that's called heat kernels. Okay. So I'm not going to explain those things. Okay. Just to form the graph, after forming the graph, form the Laplacian matrix associated. Using the Laplacian matrix, you can do a clustering. So what I'm going to, what we have to do, just I'll go to the main algorithm. Okay. The main algorithm is W is the weighted adjacency matrix of the similarity graph. Okay. Similarity graph, you know how to define. Okay. Draw the graph. Okay. Give the weights to the edges according to Sij. Okay. This will be a indirect, unweighted, simple. This is simple weighted graph. Okay. You will get a symmetric matrix again. Just to compute the usual Laplacian matrix, I'll come to this point why I'm writing unnormalized. Okay, just to compute the Laplacian matrix. Okay, first compute the k eigenvectors corresponding to the eigenvalue lambda1 up to lambda k. Okay, you form your matrix U in this way. Okay, so maybe I will draw a small picture. So U1 as a first column, U2 as a second column, and the UK as the kth column. Okay, just if you want to cluster your data points into k groups, just choose first only k columns. Okay, and then look at the row vectors. Okay, so these vectors are like now k vectors. In the beginning, like I have my data points are like n vectors. Now they are all k vectors. Okay, now for these k vectors, just I'm going to apply something called the k-means algorithm. Okay, I think that's one of the naive algorithm most of you may know. Okay, if you don't know, like you just read what is k-means algorithm. You apply k-means algorithms to this lower dimensional data points, okay, and then cluster them into k points, okay. And that cluster, in that cluster, like every cluster will contain some data points, and in that data points, like corresponding to the data point, look at the original data point in which it is represented. Okay, by original data point, I mean look at the row number. The row number will give you the identity of the original data point. Okay, so in that way you can form clusters. That's what I have written here. Okay? You can form this clusters C1, C2, up to Ck. Okay, using this by clustering these rows. Okay, then you are going to give the cluster for original data points. Okay. So there is a notion of unnormalized Laplacian. There is a notion of normalized Laplacian. Okay, I didn't include here because of the time constraint. Okay, so if you're interested, you can search for this terminology. Okay, unnormalized Laplacian, how to apply this unnormalized Laplacian for this type of machine learning. Okay. Okay, so these are all the references. Maybe just this page consists of some basic text and the papers about spectral graph theory and the application of spectral graph theory. And this is one of the influential paper on clusterings, good, bad, spectral. Now you can see that the title of the paper itself, spectral clustering, good, bad, and spectral. Spectral can be good and spectral can be bad also, depending on the data sets. Okay. And then, as I said, this spectral clustering or the bipartitioning problem, whatever I said, those are all not algorithms. Okay, they can behave in a nasty way. The data set is not a well behaved one. So, as this paper's name suggests, fundamental limitations of spectral clustering. So, this paper tells you like for what type of data this may not be very much useful. Okay, and there is one more survey by spectral clustering analysis and algorithm. If you I think most of you should identify this person. He has given a course on machine learning. I think he was very famous in Stanford. He was giving some open courses. I think he was in Stanford, Andrew Ng. And this is a lecture notes by Christian Schools. If you want to learn something more about graph partition and graph clustering, okay, you can go through our lecture notes. It's available in his page for free. And then for Daniel Spielman and this Tank, so they have identified some. They have proved that for the planar graphs and finite element measures, the spectral partitioning really works in this type of graphs. So this appeared in this prestigious journal Linear Algebra Applications in 2007. And most of the content, whatever I presented in this talk, I have taken from this lecture notes and then this tutorial on spectral clustering. Okay, this is written by Ulrich von Luxemburg. Okay. Yeah, this is highly readable. You can read it. This contains a lot of more information. So, yeah, that's all for the day. If you have any doubts, you can ask. I'm done. I hope I'm audible.
Yeah, dear participant, this is time for you. Please ask your doubt, Dr. Rajesh. Please unmute your mic and you can ask your doubt.
I hope you are able to unmute. I can see some of the more names also here.
Yes, sir. Through your talk, we have gained some overview about graph clustering. We should go through the references that you have given.
Yes.
And the proofs you have given are very clear. That's easy to follow, those proofs, sir. But doubt means, yeah, we should spend more time, at least.
Yes,
Thanks
yes,
for the
yes.
nice talk, sir.
Okay,
Thank
okay.
you.
Yeah, thank you. Yeah.
Sir Rajesh, sir, please check the actually in
chat
this
box.
box, I think we received one more question. What is the importance of eigenvalue? I think please check your
chat box. Okay. So in this setup, as I said, this is a heuristic. Okay, so in terms of symmetric matrices in general, like if you know all the eigenvalues and eigenvectors, then you know something about your matrix. You know everything about the matrix. Okay, if you know spectral theorem for symmetric matrices, or even if you don't know what is spectral theorem, in like if you have a symmetric matrix, if you know it's all its eigenvalues and eigenvectors, then you can recover your matrix completely. Okay, so here this is a heuristic. Okay, for various data, these eigenvectors are helpful in identifying these things. Okay, there are some theoretical analysis has been done. Okay, why these eigenvectors are giving like this thing. Why they are giving answer. Okay, so I think this clustering good bad. This is a good place to read. They will also they also mention something. And some of them, like the original paper where the author first introduced this method, just track to that paper. So in that papers, authors are like nicely they're explaining, because it's their duty to explain like why this method is important, or why these are important. Okay. Yeah, so that's the interesting. Suppose if we can find out some other quantity related to the matrix, if it is working really better than eigenvectors, then you can propose that as your algorithm or your heuristic. This is what my understanding. Okay, so most of the things I can tell you one thing, like for most of the applications, people are considering only the Laplacian matrix or the normalized Laplacian matrix, and then you consider the second smallest eigenvalue and the corresponding eigenvectors. Okay. Suppose if you want to compute or clustering problem also, I think if you have to group them into more than like our bipartition graph partition problem, if you have to group them into more parts, I think you can use the higher eigenvalues also. Like higher I mean lambda 3, lambda 4, and so on. Those eigenvalues also you can use. Okay. Yeah. Presentation I will share with others, and there is one more question from Tamil. So I don't know what is Parik vector. I don't know what is this Parik.
Application of Laplacian matrix.
I
think
so yeah, he's asking other than networking, like these problems, like whatever field you are choosing, even in even people from biotechnology, people are using this clustering and other things. Okay, so this is about how do you say, you have a real life problem. Okay, just you model it. Okay, and then when you are converting that into a mathematical problem, if it is possible to associate a graph with it, just associate it, and then there are a lot of heuristics and methods are available for clustering and solve those type of problems. Okay. If you're looking for some of the interesting applications inside mathematics itself, there's a mathematician Boyan Moher. So he has written a fantastic survey about applications of this Laplacian matrices of graphs. So applications of its eigenvalues of this Laplacian matrices of graphs, you can go through it. Okay. More question about eigenvalues are connected with the page rank. So page rank, it's like, you know, that's a way how Google works. There's an algorithm. Page rank algorithm is algorithm under which Google was constructed when this time. Okay, so the idea is like here I was talking about data and how to connect how to give a graph, construct a graph using data. Okay, the idea of Google is the data are like the web pages. Okay, or the vertices of the graph which you are going to construct are web pages. Okay. And you are going to connect or you are going to draw a directed arc from one web page to other web page when you have a like a outgoing link from one web page to other page. Okay. Suppose if you have web page 1 and web page 2, if there is a link, if there is a hyperlink from web page 1 to web page 2, then you are going to draw a directed edge from web page 1 to web page 2. That is vertex 1 to vertex 2. In this way, you draw your entire graph. Then compute the adjacency matrix of the graph. Okay, so I didn't define how to what is the meaning of adjacency matrix of a directed graph, but the notion is very canonical. That by canonical I mean like if you have a directed edge from I to j, keep a 1 in the ijth place. Okay, if you don't have an edge from j to i, if you don't have any directed edge, then keep 0 there. Okay, the matrix need not be a symmetric matrix, no longer a symmetric matrix, but it's a non-negative matrix. Okay, so for some technical reasons, I can explain, but I don't have time. So the authors of that, they have considered, suppose this is the adjacency matrix which you are getting from your network or the directed network, okay? Then what you have to do, you have to add this all ones matrix, okay? J stands for all ones matrix, so that after adding these two matrices, you will get a large positive matrix, entry-wise positive matrix. When you have a positive matrix, then you can apply something called Ferrand-Frobenius theorem. So that will tell you the largest eigenvalue of this matrix is positive, and you will get a positive eigenvalue corresponding to the largest eigenvalue. Okay, and to avoid some non-trivial issues, the authors, they have considered this matrix alpha into A 1 minus alpha into J. Okay, so if I'm right, I think alpha equal to 0.15. Okay, no, not 0. If I keep alpha here, I think 0.85. Okay. So you can check that what is the value of alpha. So this is the matrix they have considered. This is a entry-wise positive matrix. The largest eigenvalue of this matrix will be a positive eigenvalue, and the corresponding eigenvector. So this is the eigenvalue, largest eigenvalue, and the corresponding eigenvector. Okay, if I take it to be x, all the entries of this vector like xn, all these entries are strictly greater than 0. Okay. So now these entries are strictly greater than 0. Note that like the rows and columns of this matrix A are labeled by the web pages. Okay, has the same labeling if you apply to the rows of this vector xi, rows of this vector x. Then every entry xi corresponds to a web page. Okay. Now look at the entry which is having largest score or largest entry. That will be that web page will come first in your Google search. Okay. This is the rough idea of this is how Google was working. I think now they have added many more sophisticated thing. The question is eigenvalues are connected with web page rank. This is how eigenvalues and eigenvectors are connected with page rank. And again, I will emphasize how to compute this lambda 1. This lambda 1 and lambda, this vector x, both of them can be computed approximately using the power method. Okay. If you remember power method, okay, using power method. Okay, any other questions?
Thank you. It's a time for thanks. First and foremost, I would like to thank our director, Professor Rajiv Daraskar, and our registrar, Dr. M. Radhakrishnan, and Professor in charge Mohanan, our head of the department, Dr. Daniel, for their continuous support and encouragement of all our activities. So my special thanks to my friend and active mathematician, Dr. Rajesh, accepting our invitation and this wonderful section. So thank you, sir.
Thank you.
I extend my thanks to all the participants for this continuous event. I assure you that definitely will get some, I think, reward you. Why? Because you spent time with us. Thank you once again. And I extend our thanks to our technical support team, Siju sir and his assistant for this smooth functioning of online event. And extend my thanks to another coordinator, Dr. Asha, Minds 24. And thanks to everyone. I assure you that we will send your certificate very soon. Thank you, one and all. Thank you.
Yeah, okay. Thank you. I'll leave that.
So,
okay, see you. I'll leave.
see you. Bye.